Hello, hello. Today in this part of the series, we will be implementing some rotations to our physics objects. I've moved things a bit around and renamed some things. Instead of just an object, the physics component is now an object body, which will have the position vector, the quaternion of its rotation. It will have a velocity linearly and a rotation velocity. It will have the application of gravity like before, and it will have forces linearly speaking and the torque rotationally speaking. It will have a inverse mass and an inverse tensor inertia. Then we renamed the dampening to linear dampening and angular dampening. And I of course updated the code to hold whatever changes of names that were required. We will do an updated method here. I implemented some of the math, but we might end up in a situation where we need to do that. We will rewrite this code. We can use a namespace here where we call this old and move it into that. Nah, we'll just actually copy all of this. Whoops. And just create a section where this gets dumped into. Well, then we can see our old versions whenever we need it. And we will simply rearrange all of this. We calculate a vector, which we will call acceleration, accumulated x and force, which we will set to our object acceleration. This will apply our gravity. We'll furthermore add our force, accumulated forces. This is for the linear part. And then we the angular acceleration linear acceleration. We need to actually create a vector that takes our inertia, inverse inertia tensor, and actually transforms it into the the um, the base of the object in the world space, meaning that if it's rotated in the world space, the local axis will have changed, and therefore we need to shift around the inverse inertia tensor. Let's see. Yeah. So we would actually like a function that takes transform inertia, transform inverse inertia tensors. We would like a function that does that. It will have to take our object, since we will need yeah, I think we might restructure this eventually. Transforms, and then we want something like a steady vector of g float 3 times 3, or perhaps even just a matrix, since or rather a vector. Oh, wait a minute. Maybe I'm misunderstanding what it actually to do. Yeah, I think I am. So this is equal to the accumulated torque transformed by the inverse inertia tensor in world. Well, we actually do want that then. So yeah, we could do a g float 3 times 3 out transformed tensors, and then simply for all the objects. Simply do it like this, that instead. Since we will expect the data to come in mirrored, yeah, we would need some compile data function. And we would also want this. Let's do another version where we have the vector of g float 3 times 3 transformed tensors. And yeah, we will move the code here. Of course, do it for every object. So this will be a yeah, we can always change the function setup later on. Let's just build something and then we can adjust it later on. So yeah, I think this is also supposed to be like this instead, because we would like to be able to select the mirrored part of the transformed tensors. Maybe I do want some matrices. Maybe I want to prepare the data and just do the calculations here. Yeah. This might not be the most efficient way of doing this, but then the code would be we would like to math vector multiply matrix. We first take the objects I let's see. Yeah, maybe we want like that. Then just for the sake of naming, and then the transformed tensors I. Yeah. So this is the old code. We handle linear acceleration and torque. And we update the linear velocity, which is almost the same. Linear velocity update, which is going to be for this specific object, we will add something about the naming here. Linear axle and force accumulated angular acceleration let's do naming like this. Yeah, so it gets a bit more readable. There we go. The rotational velocity updates is going to be somewhat the same here, except we do the rotation, and then we of course add the torque. That is right. We need to name that correctly. Then we apply the drag. Apply drag. We do the same thing where we take the object velocity and instead, or rather apply the linear dampening. We do the same thing for the rotation, angular dampening, and then we update the position, which we do last. So the position gets updated with the velocity. Update linear position, updates angular position. Let's see. let's see. Let's see, let's see. Then we want to update the angular position. Which is the orientation. And the rotation. And then we want to normalize the orientation so the quaternion doesn't get outside a total length of 1, or magnitude rather. So vector, let's see, normalize. Let's do, so we set the quaternion to a normalized version. We should also update nah. And then we will clear the accumulated forces for the next frame, or for yeah, at least since we're done with applying the forces here. So yeah. So if we swap this around, I think it will stay intact, meaning that oh yeah, we could just use the Z0 instruction here. So yeah, if we change our code here in terms of integrating, if we do a vector of G matrices, Transformed inner inverse inertia tensors, and we simply add get identity matrix. Let's do that. And yeah, right now we only have one physics object. If we do like this, let's see, did I miss something? This is the one. Well, am I not supposed to overload the function? Did I? Oh, well, I haven't updated the header, of course. Which is why it doesn't know that the version got implemented. Therefore, yeah, and this should work exactly as before, because we're not updating anything, which is great, which is what we want. We want to create one with the size of the amount of physics objects. Therefore, we do like that. We would like to call our method here and we haven't added that to the header yet, so we of course need to do that. There we go, and then we can use the function. So we pass in the physics data, we pass in the, not the transforms actually, we want a, yeah, I think I'll separate I mean transform matrices from the object transforms. Maybe we want to do that. Yeah, I'm thinking about a way to restructure all of this code. For now, we will just transforms this objects. Let's see. A physics object got moved into here. Yeah. And then yeah, maybe we would want a transform index instead. Hello, welcome. Yeah, let's do that. Whenever we create the, let's see, we wait with that. Yeah, I'm unsure whether this is a great idea, but yeah, this is okay, cool. This is getting entangled a bit. Oh, wait a minute. Let's see. There we go. Yeah, I'm unsure whether we want this actually, because. Oh, wow. How exciting. Have you done any prior work like that before? Um, I mean, when we recalculate the object matrix. Oh, wow. That's impressive. You must be great at it then. Right now we can do it like dynamic objects. Yeah, I have to redesign all of this eventually. Dynamic object, physics ID. Then if it has a physics ID, we want to pair it with yeah, this is definitely have going to be redesigned. um, so we grab our uh, transform from the game objects, object transform, and we copy it, transform physics object. Let's see, we copy the transform. transforms into the actual vector of transforms, and then we pass in the pre-calculated list of transforms, and we store it in the transformed inertia tensors. All right. Then we want to pairwise transform the inertia tensor, inverse inertia tensor, by the the transform matrix. We have that as well, matrix, and we want to store that in our output. But right now we do not have a function that converts a G float of sorts, 3x3 G float. That converts the thing we have here. No, I haven't implemented text-based rendering yet. Let's see. I only have 3D models, textures, lights, collision, physics. Yeah, so I haven't really implemented the whole HUD thing yet. Right now I'm working on rotating physics-wise, so that now I swap to the player camera whenever I rotate the actual body, the camera should rotate as well. So that's yeah, then why I'm working on this. As you can see, I can move the player around, but right now the physics system doesn't support rotation. So that's what I'm implementing right now. So up here we have our different load mechanisms. I'm gonna do it not with intrinsics, but just some basic functions to get us going. Well, I guess we could do an load float 3x3, and we do a source. This is going to be let's see, do I have any this is just going to be whoops. But I guess I'll support text in the I'll of course support text in the future. In DirectX, it's probably just loading a glyph map. So you map a texture to all characters, and then you do some offsetting into that texture and load different parts of it whenever you see a specific character in a string or whatever, and you just output that to the screen, that part of the glyph texture. Let's see. So we create an identity for the last part here. The problem is that this array doesn't actually span the whole range. So we could do perhaps we could do let's see, we would have to debug this. I'm unsure whether memory-wise we would get a correct let's do 4 equal to this. First we do like that, and then maybe like this. Yeah. We could do like this. Let's see. Oh yeah, I'm stupid. Let's see, it's like that. You could do like that. Let me see, can I do this in a nicer way? Well, I don't think this works as I want it to. So yeah, for now, again, I could do better intrinsics here. But I'm not gonna do that for now. We simply are gonna copy the values like this. And then instead we will load the 4 values. And by that we create a matrix with the contents of a 3 by 3 matrix. It's a 4 by 4 matrix, but the last column is going to be like that. Yeah. Therefore, in our objects here, we can now translate it, tensor. We're gonna start by loading the data here. Let's see, pointer. There we go. So we load the data into that, then we do matrix by matrix transformation, or rather multiplication, meaning that we multiply our loaded tensor by the transform, and then we will get the relevant output. We could discard the last component here, since this will contain maybe we want a version where we multiply by the 3 times 3 matrix. Let's just see what result we end up with here. Let's save this in a matrix temp so that we can debug it, and let's just see what happens. So we get our objects, which we only have one of. We want to, yeah, okay. Right now this is empty, so it's not gonna give us anything. Let's see. Whoops. All right, that doesn't work. Let's see what happens. Is it because of transforms? Oh, it has the capacity of 0, but doesn't have any content, which is why we're crashing. Let's see. That is the mistake. Now everything should be right. So let's see the temp. Yeah. Let's see. We of course need to input actually the inverted inertia tensor, moment of inertia tensor. So I'm just gonna look up what it is for the current box here. I'm gonna move these things a bit around. Rather like this, and then we do something like this, and then we want the temp physics object to contain the inverse tensor inertia. We need to set that. Let me just look up some let's see. Let me Google inverse inertia tensor. Oh, let me do it here. Inverse inertia tensor box. I really don't want to implement a uh, uh, um, inverse matrix calculator. So we have a 3x3 matrix where we will do like that. Yeah, okay. So the result is actually the same. It's an identity matrix. I know this rotation will not be correct, but we will use it for now. There we go. Let's see. What we want our debugging to stop here. Um, yeah, I'll implement the math later on. Um, and let's just dump it. Since we want to see how it changes. Let's see. And 4. There we go. And we will do the same thing for the second column. And the third column. Since we move our object around, we want to update with that. Information every time. And right now, when I step into the debugging loop, I actually can't see it. So let's see. Let's just create a new line here. Translated inertia tensor, and then create a double line break. So we can see, okay, this really messes with the visuals. Let's just remove that. I mean, it looked awful and was hard to read. So yeah, the last one has some translation to it in terms of why, I think. Yeah, so whenever I move this, the translation here gets put into the last column as it should. But we're gonna discard that last column. We're gonna handle that in our math department. I think this was fine. Actually, as it did as it should. So in here, whenever we calculate the force, we want another version of this where we, after this, we want a vector 3 multiplied matrix 3 by 3. We simply create a matrix new 3 by 3 is equal to the old one, but we set the new 3 by 3 get the last column and set that to 0.0.0 to the identity. Yeah, since the only thing that will rather that will contain wrong information should split off last part of column 0 to 2 in case we need it elsewhere. Maybe maybe let's just do it like that, so we have a mask here somewhere. Yeah, we have a mask. Instead of doing this, we set a we simply set it to the matrix and the mask. So we copy everything except the last part of the register. And we only have to do it for that. Then we set new. Yeah, we could just do it directly instead of loading anything into register, new registers. Seems wasteful. Let's see. I think this should work properly. So we simply mask off, whoops, the last parts and set the last column to 0001, and then we return a new 3x 3x. Let's see, G matrix. Oh, rather, wait a minute, and then we call the, yeah, I totally forgot. Then we return the vector and the new 3 times 3 here in our old method. Welcome to the channel. Nice to have you, Rick. And we of course need to change that anyway. So yeah, whenever we do this, we will step into the function here. So our new thingy here is going to contain everything except the last one. I suppose. Let's see. It does copy everything, it seems. And let's check the next one. It's supposed to copy this one, where the one gets shifted. It does. And then we want to, yeah, we did that. Or rather, we will be doing that here. And then we will initialize the last part. So yeah, and then like that. We could change the mask just for debugging purposes. Let's see the real mask here, and then we swap. So we will not be taking the second item, or rather it will be faster if we just do like this, then we will see it immediately during the first operation. So let's see, our new 3 times 3 is supposed to be 0, 0 all the way, which it is because the mask cuts off the first part of the register slot. There we go. So we simply strip off the last part of each of these 4 registers, or rather for the first 3, and then we add that, and then we can do our normal vector times matrix multiplication, and we will get the right result. All right, great. So now we have actually created the needed steps to or rather translate the inverse inertia tensor by the transform. The last thing we need to do, because for instance, if we bind a key here to add some rotation, let's just do something like end. We could do a function where we would add torque torque accumulation, and we copy the torque, and we create that in our header file. There we go. Add torque. Let's see. Let's do like that. It's not implemented correctly, but yeah, we just want to see. Right now, nothing will show. We would like to output our integrated rotation, velocity, rotation, velocity. We're going to store that in a gvector_temp, just to be able to write this out more easily. Y and then C. So right now we do not have any torque. What happened? Something happened to the object. Let's see. Did I mess something up here? Well, when I copied the register, I probably, well, no. No, for some reason something odd happens. Does it? Well, anyway. Let's see. As you can see, our velocity does accumulate some force here on the rotation. Right now we won't see anything because we do not update our matrix correctly, meaning that the rotation is not actually stored correctly. Let's see. Let's do that instead. So yeah, whenever we pause the application, the collision checking probably, yeah, something happens. That's a bug. Yeah, if we pause the application too long, oh, it's the delta time. Yeah. So yeah. And the orientation, we could try to debug that. Let's see. Oh, wait a minute. Well, there we go. The orientation should change as well, which it doesn't. Let's see. Am I making a mistake somewhere? Oh well, I haven't set the I know why. I haven't set the angular drag, I think. Or rather, the angular dampening. Yeah. So as you can see, the rotation, whenever we add the rotation, we just start spinning in terms of orientation. If I add even more force, and it will of course drop as time goes because we do not have infinite rotations, but as you can see, we're able to accumulate a lot of force here. I'm just holding the button and the orientation just keeps on changing. So yeah, we're actually able to manipulate the information here and update our information. And lastly, we need a new way to calculate the object matrix. We want to store the transform. For now, I'm just gonna add something here, temp, to discern the operator overloading from our general version. And Yeah, we're gonna do a lot of math here. Um, let's see, this is the same. So the first column is supposed to have the first column is still going to take the position information, but we would like to pass over the rotation information, which is our actual quaternion. Let's see, is there a fast way of doing that? Let's see. Quaternion rotation matrix. Let's see. Okay. Yeah, so we're not gonna copy this code because our code is somewhat different, but I'm gonna use it. So instead of doing like that, let's see. First call of the matrix. So this is the real part, and then the two imaginary parts of the quaternion. Let's see. And then we have that. Then the second column, let's just do whatever here. And we need to do so row 1 0 0 0. Let me see. Am I messing this up? The first row, this is 2 0. I did that. Then the first row, second item. Huh? Am I confusing myself here? I think I am confusing myself. Let's just start over. We rearrange this. So this is the second thing column here. And this is that. And this is the third. First of the third. This is the last of the first. This is, oops, this is, wait a minute. I'm doing this wrong, right? I'm sorry. So yeah, the first one is going to be the first column. So 0, 0, 1, 0, 2, 0. This is the first column. That's fine. Oh, whoops. Then the 01, 11, 21. Yeah. And then the 02, 12, 22. Okay, I did it right. Second call, third call. And then we don't need the last one. All right. So this is our math. And I'm just gonna move it over here so I can work a bit with it. So this is the last part of the first column. This is the whole first column. Let's see. Let's do some intrinsics here. Can you do high word, low word multiplication? Because as you can see here, the first column is actually the first vector component squared, and then the second, or rather the first register entry squared and the second register entry squared added to each other. So if we could do, but the next one is crossed. Well, yeah, it's going to be hard. Yeah, I'll write out the code manually, and then I'll optimize later. Right now we just want to get something working. So the first one is equal to 2 times our object rotation 0 times itself plus next one times itself, and then in total -1. Let's do floats so that everything stays as they should. Then the next line is the second times the third component of the quaternion plus the first and the fourth. And then lastly, we have 2.0, and we have the second times the fourth plus, or rather minus, the first times the third. Yeah, and we do not overextend yet, which is great. Well, then we want 0, 1, 2, and we want to do the same down here. But for a different part of the quaternion, minus this one times, whoops, this is definitely not correct. I just realized that I was copying the wrong ones. Let's see. Times, then the last one is number 3. Yeah. Great stuff, great stuff. And then the next one. Number 2 times itself here. -1. And then there we go. And then we have to do the last one. The first times the third, or rather the second times the fourth, plus the first times the second. There we go. Let's just copy all this instead of moving it around. So that's the second, that's still the third, that's the first. And we do like that, and it's a plus all the way. There we go. And we set that to, and then the first, and -1. And instead of doing like that, we simply disable the old one because we do not need it anymore. And maybe this will work. Well, not exactly as you might see. We do have an error somewhere. Oh well. It was definitely not what I expected. Let me just check the math here. Let's see, let's remove that. Well, maybe it gets flipped by doing this. I do suspect it would. Yeah, maybe I just need to do it like a row major. Let's try that. I'm gonna comment this out and store it in case I need to use the old version. Then instead of doing the flipping here, I will simply do the exact same thing then. Okay, treat it as if it were rows. So the first one is going to be just like that, and the second is going to be the one where we 1 times 2. Well, it's actually, is it what I did? No, this is going to be minus instead. I mean 1, 2, and 0, 3 is what we're supposed to get, and then 1, 3, but plus here, and then the next one is 1, 2, plus 0, 3. The next one is also plus, and the next one is also like that. So yeah, only the signs seem to change. 1 minus 3, 0 and 2. Whoops. This of course needs to be the minus. Alright, now it's oriented in. No, it still doesn't work. I mean, that's not the problem then. Let's see, what is the quaternion actually? So we're not actually calling this method, or what? Yeah, I am. The object orientation -1. Uh, 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 if I change the rotation, yeah, it clearly doesn't work. Maybe it's my normalization method. Let's see. If I don't normalize it, what do I end up with? Let's see. The object rotation, or rather orientation. So yeah, for some reason the thing gets bugged up here. Let's see. Let's step through this. Minus linear, angular. Alright. For some reason, this gets filled with garbage values. Let's return for some reason we end up with garbage values here. For some reason, let's see. Let's see what's our acceleration actually on the object here. Torque acceleration 0. What's our force? So it's because it's initialized as garbage values. Yeah, it's not initialized. Let's initialize it as z0 and then update it. We still end up with a garbage value. and our object torque accumulation is 0. Yeah, so that's not the problem. It's inside the multiplication we have a problem. Let's step into that. And then our new thingy here. And the vector we get in here. And let's see, maybe we want to set this to that, then we return the value here. Let's try that. Or rather, the vector result. Let's try that. Maybe I need a 1 at the end anyway. On the vector here. Result also. Let's, yeah. Yeah, maybe. We could do some checks here, I think. Let's broadcast a value here. Let's try that and see if it changes anything. 0.0 ones, and then maybe, yeah, let's just test it out by setting the initialize state as 1. Let's try there. So our object torque acceleration the first time is that. Let's see the result here. Yeah, we still end up with a garbage value here. Let's see, vector multiply matrix. So for some reason the function here and then the fourth row is 1. Okay. Then we will look into the result. First part of it, 0. Oh. That is why. Uh, Whoops. Yeah, let's get out of this function and check the result here. Yeah, there we go. I think that yeah, we actually want to set it to something 1 in the end, since it's now yeah, let's test this out and see if it works. If not, we need a vec4 where the last slot is 1. Let's see. The angular. Oh, let's not step into this one anymore. And we can definitely just return this. And then the angular torque is 0. The object. Okay, let's step out of this for now. And just step into this one. Where the object orientation. Yeah, it's 0, 0, 0. Does this work then? Nope. Let's use the old one then. This is the row version. Still doesn't work entirely. I mean, now it's colliding with the bottom of the scene. Uh, uh, it ended up being totally inverted. um, which is pretty funny. Uh, yeah, so it's inside out and totally flipped. Um, I think we just adjust some signs somewhere, but where? Let's just try flipping that one, see what happens. Flipping that one, flipping that one. Oh well, it's pertaining to the doesn't it seem it's the both the let's try doing like this. Let's see. In the rotation matrix. Did it actually work when we did the row thingy? Let's just test that. I mean, yeah. It's still inverted. I mean, I'm just gonna adjust the camera here. Yeah, we're definitely having some side effects. Let's see. Object inside out rotation matrix. could flip maybe the X. Let's try that. Let's see. No, doesn't help. Then let's try to flip the Y here. Let's see. Get it back up. Peculiar. Let's just try to invert everything here. Still doesn't work. Maybe, maybe it's the initial rotation. Maybe we need an initial rotation. Orientation, rather. Yeah, maybe the quaternion is messed up. Let's see. Well, as you can see, oh, if we actually rotated, it end up in the right place. This is some fucking weird side effects. Excuse my language. So yeah, whenever the rotation so this is the row version, right? Yeah. Let's try swapping this into the column version. And let's see. Now it turns the opposite direction, I think. It definitely doesn't work as intended. see. I mean, the S is the yeah, the real part. Let's see. Let's see. So the initial orientation is supposed to be like this. Something is almost right, I feel, but definitely not. Maybe we initialize the orientation as that as well. The translation also affects the positioning. Do I change the transform for the object here? It's definitely rotated. I mean, if I set the orientation, this is the x-axis, so let's see, Equatorian. So let's do sine 1.5 divided by 2 instead. Let's see. It doesn't really change anything. Something is way off here. Let's just start with this. This is supposed to work. Right. Yeah. And if we add something like transform the x-axis, then we get flipped here. So if I negate that one, or negate these two, or just negate this one, or negate all three of them, we end up somewhere where the x coordinates get flipped. And it's not that value. Let's see. So the x, which is the first column here, so the first column, yeah, this formulation that I got was probably just wrong. Let's see. We then adjust it. We're gonna save the inverted one in case we ever want to revert back to it. And then we say our first column here is supposed to be these two things can get out of the yeah, so we subtract these two. So it's the y component squared plus is correct because we multiply by 2, but this is going to be the y component y component here, and then the c component of the quaternion. Yeah, let's just disable all these because right now we're just working on the x translation. Let's see here. This will look probably totally weird. Nope. That already fixed some of the issue. Wow. Amazing. All right, let's just check the next column. So it's the x times the y. The x times the y, which is correct here, plus the real number times the c. That is actually correct. Then the next one is rx times the c minus the real part times the c, or rather the y. Well, then that's different. Yeah. Great stuff, great stuff. Then we enable the y translation here. The first component is, let's see, that one there, yeah, it's the right sign. This is the right sign, yeah. So sorry for any flashing. Let's see, the x times the y minus the real part times the c. That is also correct, so we need to move this as well. 1.f minus, and then 2 times the x squared the x squared minus 2 times the c squared. And then the last part, 2 times the y times the c plus the real part times the x. Wow. Funny. Funny, funny. And then we enable the last part here, where we of course have to flip this 1, 0, f minus whatever, and let's check these through. So we have rx times rc multiplied by 2 plus our real part times the y, which is also correct. Then we have the y times the c minus the 2 times the real part times the x, which is also correct. Then we have 1 minus, and this is correct, and then the x squared, and then the y squared. And is that it? Yeah. We probably ended up with something from a left-handed coordinate system. For some reason, this force scales things in a weird way. Anyway, we at least have the correct orientation. If I perhaps rotate the object initially around the x-axis by 3, I think this is... Oh my god. We end up scaling instead. For some reason we end up scaling. Mm, yeah, for some reason this doesn't work as intended. Let's try something different here. Does anything happen? Let's do 80. Nothing seems to be happening. Let's do... Well, I think the first component is actually not used. Then we translate along the y. It does register the correct axis, I think. Or does it? Okay, something is at least happening. Let's see. Let's see what we do up here. We're at least getting somewhere. And let's see. Let's see. Let's see. Yeah. The updating of the rotation is not correct. Let's see. Let's see. What am I doing wrong? Let me just check the update here. This version tells me to actually flip the sign here. And then the flip the sign here. And then flip the sign here. I'm just gonna test this. Plus. Oh, wait a minute. No, I think I misread. Okay, so yeah, I think it agrees. Except for this one. Oh, wait a minute. Well, let's try to do... this is some old garbage that we aren't gonna use. Then let's try to do it in the row major aligned way. So instead we do so this is the minus. The next one is a plus. The next one here is the plus. This is fine. This one is a minus, and down here we have let me just start over here. Let me see. Yeah, this is fine. This is also fine. This is fine. This is fine. This is fine. This is actually fine. This is fine. This is supposed to be a plus. And this is fine. Let's see. Let's, instead of that, just add. Well, it doesn't really matter whether it's one way or the other. This is probably also correct. And oh well, I forgot I disabled the normalization of the rotation, which is not great. Let's see. Let's see the include. Oh, it might be the way that we're setting the quaternion actually. Let's see. Maybe. Let's not get our hopes up high. Yeah. So let's set that. Let's do a G vector. Temp, which we set to 0. Let's do a quaternion actually. 0, and then this x times duration. Let's do it like that. And then the y times the duration. And then the c times the duration. And I think it's because we do not properly do things. Yeah, so let's do quaternion temp2. Which will be the temp, let's see, math, quaternion, multiply the temp times the previous orientation. Let's do a quaternion scaled as a math vector scalar vector multiply scalar. Let's do this one and 0.5. And then we simply add, let's see, mn add ps and scaled. Let's try that instead. Well, it doesn't do anything. What if we swap the well, okay. It doesn't change anything. Let's just multiply the orientation here by a vector. Let's see. We're definitely having problems. Let's see the object. Orientation. Does it even change? Yeah, it's supposed to change. Wait a minute. Wait a minute. Oh my god, I'm so stupid. It's not the rotation, I think it's the orientation. Oh my god. The bugs are coming. Oh my god. Of course the rotation is the velocity and has nothing to do with the actual orientation of the object. That is why the whole thing changes when I change the rotation, meaning that we might, and we update the orientation through our rotation each frame, but oh my god. Let's see. Yeah, I'm gonna change this because I got impatient. So let's see. There we go. We do not get any errors because we didn't miss anyone. Oh my god. Does it work now? Whoops. I won't even get to see it. Let's just leave the old function in place. Oh my god. Look at that. Look at that. Look at that. Look at that. It's beautiful. It's beautiful. It's beautiful. Can't you see how beautiful it is? We have rotation. Houston, we have liftoff. Awesome. Really, really awesome. It was caused by an entirely stupid bug. Let's see. Now the last problem is our bounding volume doesn't get updated because it really doesn't know how to do it. I think I'll move this down to here and move this down to here. Because inside this function we cannot handle quaternions right now. But since our system supports quaternion math, we can definitely do that eventually. This will go from an axis aligned bounding volume. Let's see. Okay, the camera doesn't update yet. We also need to update that. Yeah, we need to apply different forms of calculation to transfer our data, but yeah. Meaning that, for instance, this half width needs to be updated. Let's see. Maybe if we just Quaternion sizes. Whoops. Quaternion rotate box width. Yeah, so we need the yeah, that's why whenever we add the force whenever we add the force so the vector v rotate is equal to the first the dot product of the quaternion inversed. Let's see, maybe we are able to just do like this. It probably won't work, but multiply inside a multiply. So first we let's see, objects character ID, yeah, dot, no, game objects. Let's see, do I not have the physics properties? No, I don't. That is why I'm running into trouble. Let's see. Let's see. Uh, yeah, maybe I should do oriented bounding volumes instead. They are probably way easier to handle programmatically. Yeah, I think that's our next step. I would like to dump the orientation though, just for debugging purposes. I will soon be having a break since I've been going at this for, yeah, you can't see it, but I started reading earlier today. So I've been going at it all day. Orientation quad. And then take the first part of the quaternion after it's normalized, and then the second part, the third part, and the fourth part. There we go. So right now our and as you can see, the orientation goes through the y-axis, and then it gets normalized. Yeah, so we would like to translate our whole camera by the quaternion, because right now, whenever we shift to the player camera, things aren't right. But yeah, as I've mentioned, I'll be doing a break. In terms of the YouTube series, I think we got a pretty long way in terms of implementing this awesome quaternion-based rotation system where you can, as you can see, you can invert the forces. As well. Let's see. Yeah. And the collision detection, of course, doesn't work with this new bounding volume. But yeah, I think it's a nice place to be in terms of implementing some camera rotation. Yeah, we could just do it. Let's see. Yeah. So we're gonna play around with the quaternion stuff in terms of so this updates the position. We might want to translate the whole coordinate system of the camera by the character translation. So for instance, instead of updating the position, we might want to in part update the position, but also the local coordinate systems, as they actually are part of the view matrix. Calculation each frame, which we do right here. You can see we grab the different vectors. So if we translate them as we do whenever we move the camera, as you can see down here, if we translate them by the quaternion, we would get the new coordinate system. Yeah, I'll be doing that after the break, playing around with rotating our player camera by the quaternion of the actual body. Yeah, but as I've mentioned, I'll be having a break, and if you found any of this helpful, entertaining, or even something else, feel free to comment, like, or subscribe, follow on YouTube or Twitch, or even support the channel. Hopefully I'll be seeing you around. Bye bye.